Welcome to the Distinguished Lecture Series. I'm Karen Matthews of University Video Communications. Our program is designed to enrich graduate and upper division curricula with academic presentations by top computer scientists from industry. Its speakers and topics were nominated by computer science faculty of over 50 universities. This presentation is sponsored by Intel Scientific Computers. Justin Rattner, a major contributor to the field of parallel architecture, received his master's degree in electrical engineering and computer science from Cornell University in 1972. In 1973, he joined Intel, where he managed projects in software and architecture development, including the 8048, 8080, and 8085 microprocessors. He was chief architect and manager of microprogramming for the 432. Justin is presently Director of Technology at Intel Scientific Computers, which he founded in 1984. His talk today is Architectures and Technologies for Concurrent Supercomputing. It's our pleasure to introduce Justin Rattner. Justin?
Thanks, Karen. Hi, everybody. Today I'm going to be discussing an alternative approach to very high-speed computing that's based on the use of large numbers of small processors to solve big problems in science, in engineering, and in a number of other fields. We call that approach concurrent supercomputing. I'm not going to be discussing a number of related software issues in programming languages and operating systems. But if you like what you hear today and would like to hear the rest of the story, the software part of the story, then send your cards and letters to University Video Communications, and we'll see if I can't come back and talk to you about software, operating systems, etc. for concurrent supercomputers. Let me talk a little bit now about what I'm going to say, introduce the various topics, and then get on with the rest of the presentation. First, I want to examine the reasons why we're interested in looking at alternative approaches, try to motivate the architectural decisions that we've made. Then I'm going to move on to explain the process that one goes through in developing concurrent architecture, an architecture for concurrent supercomputing. Then I'll take a look at two examples of concurrent supercomputers, an example from first-generation machines and an example from second-generation machines, and I'll talk a little bit about how they're built and some of the performance results that we've obtained from them. And then I'll move on and talk about future systems and what kinds of developments we see taking place at an architectural level and at an implementation level. When I finish that up, we'll turn the floor over to questions that have been submitted by several faculty members and hopefully be able to answer some more specific points. More and more these days, we're calling on very high-speed computers, supercomputers, to simulate real-world phenomenon. We're fast reaching the point where computers are actually able to tell us how the real world behaves faster and cheaper than we might be able to determine if we resorted to some kind of physical experiment. If you want to determine how a particular integrated circuit works or how a semiconductor process might behave, you can go into the laboratory and design the circuits or test the process. But that might take months or even years in some cases. With computers, we can model the circuits or model those processes and have an answer within a matter of a few hours or a few days. So as we call on computers to do more and more for us in modeling and in simulation, we're going to ask them to be more and more powerful. As the machines become more powerful, we'll be able to solve bigger and bigger problems. And being able to do that will mean that a number of phenomena that are really beyond our grasp today will finally be within reach. However, if we stick with a traditional approach to supercomputing, we're going to find that very few people can actually afford to use them to solve the real-world problems they're faced with. A typical supercomputer today starts at perhaps $5 million and can easily grow to be a $15, a $20, even a $25 million computer system. that costs even millions of dollars to operate. If we're going to make these techniques of computer simulation and modeling available to a much broader class of users, we're going to have to significantly reduce the cost of supercomputing. I think it's fair to say that it's really in our national interest to be able to lower the cost of this kind of computing so that all industries and other areas in health and economics can benefit from the insight that can be gained from large-scale computing. Another thing that motivates us to take an alternative approach is the fact that many of the physical phenomena that we want to model have an inherent degree of parallelism. That is, they're naturally concurrent. Lots of things are happening at the same time. Molecules are banging into one another at the same time. Particles are flying around in fluids at the same time. There's a lot of inherent parallelism in physical phenomenon. Unfortunately, traditional computers and traditional supercomputers have really failed to exploit that inherent concurrency. So we think there's a real opportunity to build machines that take advantage of the concurrency found in the real world. Now let's look at the design decisions that an architect is faced with when considering the various points in a concurrent architecture. The first thing is to decide on the overall architectural approach. Once that's decided, then we can get down to more specific details like the choice of processor or processors, as may be the case. We can look at the memory organization and the memory technologies. And finally, something that's going to be very important is the means for allowing the processors in the system to communicate. And we'll talk a lot about communication in the rest of the talk. Okay, looking at these decisions now, starting out with the idea that we want to build a supercomputer. I'm really going back to basics here. We have two fundamental choices. One, we can take a parallel approach or a concurrent approach where we're going to call on some number of processors to get the computing job done. Or we can take a sequential approach, as has been done with traditional supercomputers, machines like the Cray 1 and similar supercomputers. Or we can look at a parallel processing approach. The problem we're facing with the sequential approach is that we're running into serious physical limits. The speed of light is starting to constrain us. The problems of heat dissipation in these very high-speed machines makes it more and more difficult to look at a sequential approach. And we can actually see within the next 10 years or so building machines that are literally at the physical limit. If we want to build machines that are faster than sequential machines, we have to go parallel. So we'll assume that's the decision we're going to take. Given that we want to take a parallel approach, we have a number of choices in terms of processors. We can tie together some small number of very expensive processors. That's the approach that Cray's taken in the XMP series and continues to take in the Cray 2 and soon in the Cray 3. The problem is we're really not increasing the number of processors very, very quickly, yet we're increasing the price of the system dramatically. Each one of those big, powerful processors is very expensive. That forces us or drives us to consider many low-cost processors as an alternative. And here we're talking about the kind of processors that are used in personal computers and workstations. It turns out that if you look at the cost per MIP or the cost per floating point operation or million floating point operations, megaflops, this is the cheapest form of computing available. So it makes a lot of sense to look at that approach as the means for generating the kind of processing power we're looking for. As soon as we've decided on the lots of low-cost processor approach, then we need to take a look at the memory organization. Now, if we're trying to keep the machine as much like conventional machines, sequential machines, as possible, we want to consider shared memory. And shared memory is relatively attractive for small numbers of processors. And machines have been built out of low-cost processors that use shared memory. I'm talking about machines like the Encore Multimax and the Sequent Balance and the newer Symmetry machine. And those are reasonable machines for processor counts, let's say, of several dozen. But if we really want to build large-scale systems with tremendous amounts of processing power, we really can't consider a shared memory approach, at least a physically shared memory approach. We run into too many bottlenecks. We might run into bus limitations. We might simply saturate a bus with all the requests from the processors to either a single memory or multiple memory units, or we may run out of memory bandwidth. The alternative is to look at a distributed memory approach. Now, that's an approach where each processor is given its own memory, its own private or local memory. And then some technique is provided, we'll talk about it in just a second, for allowing the processors to communicate with one another. Well, the distributed memory approach has been used in a number of machines now. It's being used in a number of hypercube machines, and I'll be talking more about those. It's being used in some switch-based machines like the IBM RP3 and the BBN Butterfly. So distributed memory is really the architecture, the memory organization of choice when you want to connect a large number of processors. Okay, so now we've said distributed memory is the way to go because we want to have a lot of processors. How do we come up with a scheme for allowing these various processor and memory nodes, as we call them, to communicate? Well, we have a couple of choices. We could try to preserve the same kind of model that we have in a shared memory system, and I call that a variable sharing model, where a program running on one processor can access the memory of another processor. It could somehow reach through some kind of network and gain access to that memory. Or we can take a message passing approach. There are examples of machines that have distributed memory that have taken the variable sharing approach. Again, our examples are the IBM RP3 and the BBN Butterfly. The problem is with those machines, you pay an awful lot in their switches to get the kind of high-performance access you need to do a single read or write from memory, and you don't really use that hardware efficiently. A lot of it sits around not doing anything while the processors are off communicating with their local memories. And those networks that support the kind of variable sharing model I'm talking about are also quite expensive to build. In fact, IBM reported that the kind of switches you need to do a good job supporting the variable sharing model cost between 6 and 20 times as much as the switches that you'd use for a message passing machine. Well, all of those economic ideas really drive us in the direction of a message passing approach to communication between these various processor and memory nodes. Message passing communication can be done quite efficiently and quite simply in hardware, and it turns out that many problems decompose themselves very naturally with a message passing model. If you think of a very simple case, let's say, of modeling the particles in some kind of fluid, the interaction between the particles can be viewed as the exchange of messages between those particles. So by sending and receiving messages between particles, we're actually modeling the physical interactions of those particles. So message passing looks like the way to go as far as we're concerned. Well, let me kind of consolidate all of that into a conceptual model that I want you to have pretty much for the rest of the talk. We're talking about message passing concurrent computers here with processor memory nodes, this idea of distributed memory. Each processor has its own memory. And then some arbitrary number of these processor memory pairs or nodes. Might be talking about hundreds or even thousands, possibly tens of thousands. And then this communication network, which I've shown in the form of a cloud here. We're going to have a lot more to say about the structure of this communication network as we move along. Well, if I can just pause for a minute and reflect on that architectural approach, let me suggest that the real issue is going to be how do we structure the communication network. assuming for a minute that we can come up with a way to do that and do that effectively, what are we going to gain from these architectures? Well, we think we're going to gain a lot of things. We hope we're all going to gain something. First, we think we're going to see a tremendous improvement in price performance. And we estimate that as being anywhere from a factor of 10 to a factor of 100 over conventional approaches to supercomputing. We think we're also going to be capable of building the very fastest machines that are possible. Once we hit that sequential limit, we start to go parallel, and we're adding a number of processors, it's going to be very clear that the fastest machines are simply those machines with the largest number of processors. And finally, we'll get something that we don't even get from conventional approaches, and that's a broad performance range. We'll really be able to configure machines with small numbers of nodes or large numbers of nodes or some number of nodes in between and really tune the machine to the kind of processing power required. Okay, let's look at these communication networks now and see what choices we have. Well, we could connect them in a very simple fashion, as illustrated here, what we've called the linear chain. Now, I want to make sure you don't confuse this with a linear bus architecture. The dots in this illustration represent our little processor memory nodes, and the lines are these communication channels. They're actually bidirectional, or more exactly, they're full duplex communication channels. This turns out to be a fairly decent way to connect the nodes, assuming you don't try to connect too many of them. And machines have been built using this connection structure. I'm thinking now of the Watt loop machine done at the University of Waterloo by Neil Oslin. Quite effective in its particular range of applications, but not too many processors. I think 64 in the case of the Watt loop. Well, if we're really reactionary about our network design, we could consider a fully connected graph. And that's a structure in which every node is connected to every other node. It doesn't look too bad here in the graphic, but imagine connecting hundreds or even thousands of nodes like this. You just have wires every place, and it would be virtually impossible to package physically and very difficult to debug. So we look for an engineering trade-off, really, in the design of the network. And the network that's shown itself to be extremely effective and a really good balance between the simple linear graph and the completely connected graph is the hypercube. The one nice property about the hypercube is the fact that communication costs tend to grow logarithmically as opposed to linearly. And that's sort of a happy medium between the unity costs of the fully connected graph. Turns out hypercubes have really been chosen for all of the highly concurrent machines, the hypercubes that have been built by Intel, built by N-Cube, Amatec, Floating Point, and even the connection machines from Thinking Machines use a hypercube communication network. So that's a pretty popular one. Let's take a look now at a first-generation hypercube. I happen to bring one with me here today. It wasn't too hard. It's a good thing I don't work for Cray. This would have been really hard to get here. But this machine is pretty light, only weighs 100 or so pounds. One of these towers contains up to 32 nodes, or it can be configured with 16 nodes. I'll show you that in just a second. And then we can stack them together in a line to connect up to 128 nodes. All right? And all the cables and wires for the network are hidden within the cabinet. The only thing we have is the power cord. Let me stand up for just a second. The display panel here shows the node activity. And inside, you see the nodes themselves. In the Intel hypercube, the IPSC, the nodes are equivalent to boards. So we have a node here. I'll just slide out a little bit. That contains the processor and the memory and the communication hardware that's necessary to implement the hypercube. It turns out if that isn't enough memory, if there isn't enough memory on that node board, we can add memory by plugging in a second card in the adjacent slot. And we'll talk about that a little bit in just a little bit. And if together or apart that's not enough processing power, we can also connect to a node a vector processor that has very high floating point performance, and we'll take a look at that in just a second. The upper part of the cabinet here contains the power supplies and cooling fans and so forth. All right, let's look at one of these hypercube nodes from the Intel first generation concurrent supercomputer, the IPSC. This is the node board here, and the node board contains its processor. That's an 8286 microprocessor, and its floating point unit, the 8287. It also contains its local distributed memory. There's a half a megabyte of memory here. And then it has this bank of communication controllers. There are 8 of them, 7 to wire the hypercube in up to 128 nodes, and an 8th one to allow the node to communicate with the outside world. Now, half a megabyte of memory is really not a lot of memory to work with, and a lot of people who started using the IPSC wanted more. So we used this idea of plugging a card into an adjacent slot to take the memory up by a factor of 9. And this card here is the memory board, and it contains 4 megabytes of memory, which is buffered by this cache located here on the board. And we simply plug these two boards together, and we've got a 4.5 megabyte node. But that's still not very much processing power, even though it's a lot of memory power. All right? To get more processing power, we've gone to the idea of vector processing, an idea that we borrowed from traditional supercomputers. And this is the vector processor. And there can be one of these attached to every node in the hypercube. And the vector processor has its own floating point units, its special vector memory here. There's a megabyte of vector memory, and its own independent program sequencer. Now, together, that forms a very powerful node. A peak performance capability of 20 megaflops at 32 bits, and about 6.6 megaflops at 64 bits. Well, let's see what kind of performance you can get with that kind of hardware. Well, fortunately, within the last few months, a number of commercial applications have reached the marketplace for the IPSC, the vector IPSC, what we call the IPSC VX, and we're able to compare the performance obtained on those applications with the performance obtained on other machines. One of those applications is called Necton. It comes from Nectronics Inc. of Cambridge, Massachusetts, and it's a fluid dynamics and heat transfer code. It does all the sorts of things that you'd expect a fluid dynamics code to do. It solves the Navier-Stokes equation and also solves the energy equations in order to do the heat transfer. It uses highly stable numerical methods, and I wanted to emphasize that because we're not taking any shortcuts here in order to get the most processing power out of the nodes. This is a very reliable piece of software. It gets the right answer, and there are no shortcuts. Finally, Necton is able to handle both the 2- and 3-dimensional fluid dynamics problems. And that emphasizes the idea that I was trying to make earlier, that as these machines get more powerful, we can go for more detail in our problems. And going into the 3rd dimension is an example of that. Well, let's see how Necton does. We'll start by looking at a typical super mini computer, the DEC VAX, and I've chosen the VAX 8600 here as an example of sort of a mid-range machine in the VAX line. If you ask your local DEC salesman, he'll tell you you can have one for about $600,000. And running Necton, you'll get about 0.8 of a megaflop. Now, we'll use the VAX as our price-performance reference. I'm concerned here about price performance because, again, one of our objectives and one of our motivations was to lower the cost of supercomputing by using concurrency, and price performance is going to be the way we'll measure that. All right, let's bring up our canonical supercomputer here, the Cray XMP Model 14. That means it's got 1 processor and 4 megawords of memory. You can have one of those for a cool $5.5 million, plus the building and the cooling tower to keep the machine from burning up. Necton will deliver about 80 megaflops running Necton, and that represents about an 11-fold price-performance improvement. So clearly, there is good value in supercomputers, even traditional ones, if you can afford it. And that's really the issue here. Well, an IPSC VXD5, that's a 32-node vector hypercube, nodes configured with the standard node, the 8286, and its vector coprocessor. That sells for a little over $500,000 and yet delivers almost as much performance as the XMP14, about 70 megaflops. Most significantly, the price performance is about a factor of 9, a little better than a factor of 9 greater than the Cray XMP. So almost that factor of 10 here running the Necton fluid dynamics code that we were talking about being a major benefit to concurrent architecture. So this is a real application now. Necton runs on all these machines, gets the same answers, has the same interactive interface with users. So I think it's fair to say that even the first generation concurrent supercomputers are capable of true supercomputer performance and do deliver the benefit of greatly improved price performance. Well, even though Necton, the results from Necton are very pleasing, we were certainly delighted when Nectonics reported them to us. Not all applications have been as successful. And let's take a look at one that really has given us a lot of trouble. That's the two-dimensional fast Fourier transform. Now, this is an algorithm, really, not so much an application, that's widely used in image processing, filtering, and various other kinds of image enhancement processes. It's something that's easily pipelined and vectorized, and that means it's going to do very well on conventional supercomputer architectures or on highly specialized architectures. The problem is this is a real bear for concurrent architectures. And let's try to understand why that is. To understand it, we're first going to have to drop into a little more detail and talk about how communication actually takes place in the hypercube. So let's take a look at how we perform the two-dimensional FFT on a concurrent supercomputer. First, we distribute the data in rows to the various nodes. If we're doing a 1,000-point by 1,000-point transform, that means that each node in a 32-node hypercube would get 32 of those rows. We perform the FFT on those rows. All those nodes are working in parallel, so we're running maximum performance. Then we have to transpose the data. We literally have to move the data around between the nodes so that the old rows are the new columns now. And we call that the row-column transpose. Once the data is in place, then we can perform that FFT again, that one-dimensional FFT, totally in parallel. If you look at the performance here, you can see that while we're performing the FFT step, we're running at 320 megaflops, 10 megaflops on each node in a 32-node system. But the row-column transpose takes us 4.2 seconds, and during that time, we're not executing any floating point operations, so we get a big 0 for that. When you look at the totals, you see that we've dropped tremendously in terms of average megaflops from 320 down to 23, and the time is almost totally dominated by the row-column transpose step. Well, that's clearly where we want to focus our efforts. Let's look now at how these first-generation message-passing machines deal with the problem of transposing the data. Communication in these machines is based on a technique known as store and forward message passing. And we've got a simple illustration here. This is a little 4-node hypercube. The nodes are these rectangles. The shaded areas here represent the communications controllers, as I showed you on the node board. And we'll also assume that it includes the system buffers for the messages and some of the operating system logic to deal with them. In our example here, the node 0 has a message it wants to send to node 3. Now you'll notice that those nodes are not directly connected because it's a hypercube. And we're going to have to pass through an intervening node in order to deliver the message. Well, the first thing we do is transmit the message over one of our hypercube channels, and you can see here that the message to node 3 has moved into node 1, and it's being held in one of the system buffers. When it gets here, the operating system looks at it and makes a decision as to whether it can hand it to an application here or whether it needs to transmit it to another node. Of course, that's the case. We're going to move this message to node 3. So in the final step, node 1 transmits the message that it's relaying now from node 0 to node 3, and the process is complete. We call each one of these stages a hop, and I'll probably use that term as I move along. I'll talk about multi-hop messages. So that's how the message passing is performed in the first generation machines. Now look what happens in the 2D FFT. Every node needs to exchange information with every other node. We've got to perform that row-column transpose. So node 0 has messages for nodes 1, 2, and 3. Node 3 has messages for nodes 1, 2, and 0. They've all completed the pass on the rows at the same time. They all want to transmit at the same time, and the network just goes into saturation. What's more is the operating systems that are dealing with the messages, that are performing the store and forward step, can only handle one message at a time. So this thing really moves very slowly as the messages get distributed around the system. Well, algorithms like this that were so totally dominated by communication performance were really one of the motivating factors in the design of our second generation systems, and I think that'll be true for other manufacturers. So that was our top goal, and we really spent a lot of time thinking about how to do this, and we were very closely involved with our research partners at the California Institute of Technology. And we were fortunate that several years ago, in fact, Bill Dally and Chuck Seitz came up with an idea for improving message passing in concurrent architectures that we've incorporated into the second generation machines. They called their technique wormhole routing because of the way messages tend to worm their way around the network. In the Intel hypercubes, in the second generation hypercube, we refer to the technique as direct connect routing, and let me explain to you how it works. We've replaced those communication controllers and system buffers and operating system logic now with hardware. And in our little illustration here, the message interface of the node looks like a switch, and in fact that's what it is. It's a very specialized switching network. If we want to send a message now from node 0 to node 3, the same example we used before, rather than setting up for the store and forward operation, what we want to do is close switches. This is the routing process that I was talking about. And the hardware in a direct connect routing system is smart enough to do that on its own. It doesn't require any software intervention. The first thing it does is actually construct a path or a route through the entire network from the sender to the receiver. And as you can see here, we've closed a switch in node 1 and closed another switch in node 3 so that when we transmit the message, it will move directly through this hardware to the destination node. And it does that at very high speed because it's dealing entirely in hardware. None of the store and forward activities that we had to deal with in the first generation machines. The data is actually pipelined through the network, so we get very high bandwidth. And here you can see the message is now deposited in node 3, completing the process. As the tail of the message moves through node 1, the switches actually open, and that frees the channels for other communications. Well, there are a number of benefits that we get from direct connect routing. One of them is lower message latency. That is the startup time for one node to send a message to another node. It's improved somewhat by higher performance hardware to a near neighbor, but it's greatly improved to nearest neighbors because of this idea of closing switches and building a full route. We also get higher channel bandwidth because of pipelining. We're able to move that data over the full route at hardware speeds and never suffer any of the delays from software. We also get greater network throughput. It turns out that these direct connect routers can actually move up to 8 messages through themselves simultaneously. So the total number of messages that are moving through the network is much greater than it is in a store and forward system. And finally, we get nearly constant communication bandwidth. It's almost impossible for a programmer to determine the difference in the time it takes to send a message to a near neighbor and the time it takes to send a message to a distant neighbor. And that's much closer to the ideal model of a message-passing concurrent computer. And we think that's going to simplify the programming of these second-generation machines considerably. Well, we had a number of other goals in these machines. We wanted to expand memory capacity. Everybody wants more memory. It's as true in concurrent supercomputers as it is in any other kind of computer. We wanted to move from the 16-bit node architecture or implementations in the first generation machines to 32-bit nodes. And we also wanted to preserve application portability. We wanted all this experience that had been built up with first generation systems to carry over to second generation systems. Well, let's take a look at a second generation system. And it turns out I now have one of those sitting next to me. And as you can see, it looks exactly like one of our first generation systems. This is an IPSC2. And that's true because the two machines are actually electrically and physically compatible. We use the same board form factors, cabinets, power supplies, and so on. What we've really gone in and done is change the structure of the node. And I have one of the new nodes here. Let me set this down for a second. This is a second generation IPSC2 node, and it's got its processor again, an 8386, and its floating point unit, an 8387. This is a DMA controller down here. Its memory is implemented in the form of these surface mount 1 megabit memory parts that attaches a daughter card to the node board. And we can get up to 8 megabytes in this configuration. Remember, we only had half a megabyte on a first generation node, so that's a tremendous increase in storage capacity. And if that still isn't enough, we can actually stack these memory modules. And here's another one of those 8 megabyte modules, and you can actually pick that up and lock it down on this connector and have a 16 megabyte node. If you want higher performance, of course, than you can get from a 386, 387, you still have the option of going to the vector node. This is the same vector node that we used in the first generation system, so it's all compatible and all the software works. The real magic in the second generation machine is down here, and that's the direct connect module, and that's implemented in very high speed gate array logic. And it's with this logic that we implement those switches that close and open in response to messages moving through the network. And that's also on this little daughter card, like the memory module is, so we can change that as the technology evolves. Well, let's look at what impact these improvements in the second generation concurrent supercomputers have on performance. And we'll go back to our fluid dynamics example with Necton. You can see Necton performance is up significantly, almost 50%, in the second generation machine, same size machine, same number of nodes. But where we really get the benefit is in two-dimensional fast Fourier transform, our communication bottleneck. We're up here by an order of magnitude, a factor of 10 improvement, from a lowly 23 megaflops to a very respectable 230 megaflops on a 32-node vector machine. Finally, I've added one other benchmark, if you will, here to try to illustrate that these machines are also capable of very high speed symbolic computing, not just high-speed numeric computing. And the benchmark is a fairly popular one for Lisp systems. It's called the Triangle benchmark. And Triangle is this little board game that you're probably familiar with. I used to find these in the pancake houses around my neighborhood. And the idea here is to try to jump the pegs and leave only one when you've finished the game. And after a while, you get good at that. What we ask the computer to do is find all the possible solutions. On a first-generation machine, that takes a little over 37 seconds. But on a second-generation machine, it's improved by a factor of 4. It's down to 9.4 seconds. So there's a symbolic application that we can handle on these machines, and the second-generation communication structures and processor improvements benefit it as well. So overall, we're looking at between a 3- and 5-fold improvement in these systems. Well, let me review a little bit now these various machines. The first generation machines used hypercube networks. They relied on software routing and store and forward communications. And those channels were bit serial in nature. That is, they only passed one bit at a time, although they did that in each direction, as I said, full duplex channels. The first generation nodes look very much like a typical microcomputer system with a CPU, a memory, and a DMA, and a specialized I/O structure, in this case the hypercube channels. Okay, so a fairly simple and fairly common structure. The second generation machines retain the hypercube network, but now we've moved to hardware routing, the direct connect routing I talked about, with pipeline transmission. But we've retained the idea of bit serial channels. The nodes are a bit more sophisticated, same CPU, memory, and DMA structure, but now we've replaced all those communication controllers with this specialized block of router hardware. And I think you'll see that in other second-generation systems, not just those from Intel, as various people move to the higher performance hardware technologies here. Well, just a few words on next-generation systems. I think we're going to see a significant change in the structure of the networks for second-generation systems. Continued research at Caltech has shown that low-dimensional networks, such as the 2D mesh I've shown here, or two-dimensional torus, are actually more effective, make better use of the physical wires in the system than hypercubes do. And at least in simulation thus far, this looks like a very attractive way to go. When you trade a high-dimensional hypercube for a low-dimensional network like a mesh, you can actually put more of your wires into the communication channels. And we expect that these networks will have byte-wide channels as opposed to bit serial channels. We'll still be using hardware routing and pipeline transmission, and we expect them to incorporate some kind of broadcast facility. That's a little tricky to do, but it'll benefit a lot of applications where one node has to let every other node know what it's doing. Now, the node architectures are going to change significantly, we think. They're going to take more of a memory, they're going to have more of a memory-centric organization, and I've illustrated that here with a multi-port memory. And the processing units are going to get more specialized as well. And we'll make a lot more use of application-specific silicon in this case. We'll have nodes that are general purpose, like the ones we have today, and numeric nodes, like our vector processor. But we're almost certain to introduce nodes that are particularly adept at symbolic processing, specialized nodes for input-output, and we can imagine a number of other kinds of specialized processing units that we want to introduce in these machines, all to get the best cost performance out of the machine possible. Now, the routers in these machines will very likely be integrated onto a single chip. So with that structure, all we need is to connect the dots, so to speak. And we're going to do that with specialized processors for sending and receiving messages. And these engines, if you will take messages out of the network. Again, the routers will have already decided that the message is for this particular node. The receive processor will put it in memory, notify the application engine that the message is available. It'll perform its task and generate any replies. So much more specialized silicon all around in our next generation node architectures. Well, when you've got systems with lots of specialized silicon in them, lots of application-specific nodes, you can build really a new class of large-scale system of a heterogeneous nature where you're mixing and matching processors. Here I've shown a simple system with specialized nodes for file processing, symbolic computing, numeric computing, display, image processing, and on, just mixing and matching the modules, the nodes in this case, to build the optimal machine. And I can expand that concept because these networks are easily scaled to incorporate other specialized processing needs as my applications grow in time. And here I added signal processing, a gateway to a local area network. So in the future, we expect to see very large systems with all sorts of different nodes performing a whole range of very large-scale computing tasks. Thank you.
I'm Judith Lemon from University Video Communications, and we now have some faculty questions for Justin. From Yale University, if message passing models are not what programmers want, can Intel machines present different kinds of models for the user?
Well, that's interesting. One of the things we've been looking at recently is how to support a shared memory model. We talked about shared memory as being the alternative memory organization and shared variables as being the alternative communication technique. So one of the things we've been studying is techniques which use the memory management hardware on the second generation machines. The 8386s come with fairly powerful memory management units, and it's possible to create the illusion of shared memory in the machine by using the memory management hardware. The technique is called global virtual memory. It was, I guess, first developed at Yale by Kai Lee, who's now at Princeton. The University of Delaware has proposed similar techniques. So we're going to be exploring that in the near future, and we may be able to offer it as an alternative model. We still like message passing. We think it's a very natural way to program, but there are people who prefer shared memory, so we hope to be able to offer them that alternative as well.
Question number 2 comes from the Massachusetts Institute of Technology. Justin, what is the trade-off between distributed memory architectures such as Hypercube and shared memory architectures such as Sequent and Encore machines?
Well, I think it's primarily, where it has been primarily, a trade-off between cost effectiveness and ease of use. I think the Hypercube machines have shown themselves to be more cost effective. Their nodes are cheaper, the systems are cheaper on a per processor basis. But I think the shared memory machines like Encore and Sequent have shown themselves to be somewhat easier to program. I think primarily due to the fact that their software environments were or are a little more mature than the ones for the message passing machines. But I think with the advent of second generation concurrent machines and looking to the future, the differences between the ease of use of the two types of systems will begin to disappear. And I think the advantages of the message passing architectures will quickly overwhelm the perceived programming simplicities of the shared memory machines, and most machines in the future will have that kind of message passing network at their heart. So I think in the future that trade-off will disappear.
From the California Institute of Technology, what are the prospects for developing automatic translation programs from existing dusty decks to message passing concurrent programs?
I'm not personally very optimistic about the possibility of having translators that will go from an old Fortran program, the classic dusty deck, to a parallel or a concurrent program. But you might say we're hedging our bets. We're actually supporting research around the country in those systems. Among the people working on that problem is Ken Kennedy and his group at Rice University. And I understand they're going to be publishing some results soon, so we should see. But really, our whole approach and sort of the premise of our business is that the cost performance advantages and the ultimate performance of these systems will be so great as to motivate people to convert the programs for concurrent operation and not wait for automatic translation.
From the University of Southern California, can you comment on any new modes of problem solving which very large-scale distributed architectures will make possible?
Well, I think that's one of the things that the advent of these highly parallel machines has stimulated. I think a number of people are looking at new problem-solving paradigms for large-scale systems and distributed systems in particular. It seems very appropriate now with systems of such a large scale to look at programming approaches that deal with very large-scale problems. One of the issues that that we're very concerned about and hope to see a lot of advancement in the near future is the need to combine artificial intelligence techniques with numeric computing techniques, something we call expert computation. And those are so radically different in their nature that it's going to take really a new programming model to make those two things work effectively together. But people are making progress there. People are thinking about applications for those kind of fused systems, and I think we'll see a lot of progress very shortly.
Okay. From the University of Minnesota Institute of Technology, any comments on applications of supercomputers for rapid solution of large sparse linear programs?
Well, I'm glad we got a question on large sparse systems. It's one of the areas that I think have given the distributed memory machines a lot of trouble thus far. The early results that were reported were not very impressive. I think they were similar to the early results with fast Fourier transforms, the 2D transforms we talked about. But more recently, people have attacked specific problems with sparse matrices. Bob Lucas at Stanford, in his work on VLSI device and process simulation, developed a very specific technique, given the structure of the sparse matrices for that problem, that seems quite effective. And I think other people are working on the general problems. As the communication networks improve, the performance with sparse matrices will improve. And there are just a host of applications that will benefit from that. Not only the kind of semiconductor modeling I was talking about, but I think a lot of financial problems, a lot of problems in circuit simulation, just on and on. So the future generation of machines that I was talking about with these very high performance networks should do quite well with sparse matrices. We put it at the top of our list and want to make sure the machines do a good job with them.
Okay, and for your last question, Hypercube represents a significant transfer of university research to a commercial product. What are your thoughts on what does it take to move an idea from a university to the marketplace?
Well, we actually spend quite a lot of our time maintaining our relationships with faculty members and graduate students around the country. Intel has supported a lot of work in parallel processing. I think if you look at the period between 1980 and 1984, we probably had close to a dozen different projects that we were involved with around the country. That has the benefit of creating the right kind of relationships with the researchers that you need, and it helps you sort out the good research from the not so good research, which is very important. In particular, we look for people who are attacking the kinds of problems that are going to have broad commercial interest. We like to work with people who have some sensitivity to commercial needs, so that there isn't a tremendous gap in moving the technology along. It's very nice to have prototypes. Even if you've got all that, and it does occur frequently enough, there's still a lot of work to bring an idea to market. You have to go to the market, you have to talk to the users, find out what they want, find out what sorts of things are appropriate in the real world, and then bridge the gap or provide the glue, what have you. And there's a lot of engineering that goes on. I don't think all the researchers appreciate, in fact, how much engineering has to take place and how much documentation has to take place between an idea on campus and a product in the marketplace. But we've done a lot of it at Intel, not just in the systems area, also in the semiconductor area, and we think it's an effective way of working, and we'll continue to do it.
Thank you very much, Justin.
My pleasure.
Thank you. And thank you for joining us today. We invite your comments and questions on this presentation, and we hope you will nominate future speakers and topics. You will remember that Justin promised to do software if requested, and for the purpose, we've provided postcards under the label of your video cassette case. Thank you very much.